Okay. So to avoid piping, we are going to increase the length of the flow, or we have to provide uh, a filter, a loaded filter instrument, or per so how to design filter? So there is no there is not a specified procedure to design the filter, but there are some criterias using which we can design the filter, or using which we can design the, or using which we can select the materials to construct the filter. Okay, the conditions for proper selection of material. The first one is the size of the voids in the filter material should be small enough to hold the larger particles of protected material in place. That means the voids, okay, the small materials should not pass through the voids. Okay, the voids must be small enough as to hold the particles in place. If the voids are big enough, then the particle itself will enter the voids, and there will be no, and the voids will be closed. The water won't be able to flow through the filter. Okay, the filter material should have high permeability. Okay, to prevent the buildup of the seepage forces. Okay, and hydrostatic pressures in the filter. So the filter, to make the water flow through it, it must have high permeability. Usually, the filters, uh, there are different layers in the filter. Okay. Okay. So a dam filter, okay, it will have different layers. Okay. Okay. This is a filter. Okay. At the starting, the filter, the material used is finer, and as you go through the depth of the filter, the size of the material is going to increase. The first layer is fine sand, the next layer is coarse sand, the next layer is gravel. So the particle size is increasing through the layers. Uh, that is okay. If this is the filter, there are different layers in the filter. First layer, and this is my second layer, third layer. First layer, let's say it is fine sand. Okay. In the second layer, you will have particles whose size is more than fine sand. Let's say coarse sand. Okay. In the next layer, the particle size will be bigger than that of the coarse sand. Let's say gravel. So you have to make sure that
Stress due to force as weight as soil mass is the as soil mass is the huge collection of soil particles. These soil they exert force as weight downwards on the other particles. Weight is a force and we represent it in Newton or kilonewton. These soil grains, due to their own weight, gets pushed by all the surrounding particles and exert force on each other, which is represented by a quantity we call stress. Stress is defined as the force divided by the area over which it applies. It expresses the internal forces that particles of a material exert on each other. The stress is a vector quantity, just like the force. So we can decompose it into normal stress and shear stress. The stress developed on a surface because of the force component perpendicular to its area is called normal stress. N is the force component normal to the surface of area A. And the stress developed in the surface because of the force component tangential to its area is called shear stress. When a soil mass is subjected to an external load, such as load due to overlying structure, the state of stress within the soil changes, and that may affect the stability of the soil mass, and deformations may occur to the surrounding soil. So, it is necessary to analyze the stresses within the soil mass. Total stress on an element in the soil is equal to the force on that element divided by the area of that element over which the force is acting. Force on that element, everything that element of overlying structure, we can understand this stress as the pressure of overburden. This total stress in the soil is shared by the two components of the soil mass. Part of the stress is shared by the soil grains that are in contact with each other by their grain to grain force transfer, which is called effective stress. And part of the stress is shared by other component, water present in the voids of the soil structure. This is called pore water pressure. Let us consider a soil mass which is fully saturated. Imagine this soil experiences the force capital P at some point in soil because of its own weight. This force is resisted partly by the interparticle forces at the point of contact and partly by the force exerted by water available in pores, that is, pore water pressure force. Now take an imaginary plane XX at any level in the soil mass, which passes through all the points of contact between soil particles that lie in this plane. This plane looks wavy on the small scale, but for all practical purpose, on the mass scale, we can consider it perfectly plane. We will try to analyze the forces on this plane. The total normal stress on this plane can be given as total normal force acting on the plane divided by the area of the plane, let's say capital A. The interparticle forces are random in magnitude and direction throughout the soil mass. So on this plane, at every point of contact, we can resolve them into normal and tangential components. Let's say the normal component of the force acting on a particle is capital N. So sum of all these normal forces is summation of all N. The water filled in the voids of the soil also exerts pressure on the soil grains in all the directions as Pascal's law suggests. This exerted pressure by the pore water is called pore water pressure. This pressure exerted by water also due to overlying. This by inserting a standpipe or tube inside the soil at the location where we want to measure the pressure. Let's say the pore water pressure is small u at the plane. So the total force offered by pore water pressure force is U multiplied by the area of voids in which water is present in this plane. We say that area as AW. Let's say the sum of all pore water pressure forces is summation U. Now by applying equation of equilibrium on the plane XX, we can write that total normal force acting on this plane is equal to the sum of all normal interparticle forces and pore water pressure force. Divide the equation by a whole cross-sectional area capital A of the plane. We can write pore water pressure force as this. If we notice the area of contact of soil particles, let's say AS, is very small, and almost all the area of this plane is covered by the area of voids, AW. So in our equation, these can be considered almost equal. And this value we have already noted is the total normal stress on the area. So we get this. In this equation, this quantity is called effective stress. It is generally denoted by sigma prime or sigma bar. We can say that effective stress is the pressure transmitted through particles' contact with each other. It must be noted that effective stress is equal to the total normal force transmitted at the points of contact divided by the total area of the plane, which includes the area of voids as well that are occupied by water. This effective stress is much smaller than the actual contact stress, which will be total normal force that is transmitted at the points of contact divided by actual contact area only. This quantity will be huge. So the effective stress has no physical meaning and therefore it cannot be measured directly. But it is deducted from two physical and measurable quantities, total stress and pore water pressure. But still, effective stress is very important and useful for the soil engineers. It has been observed experimentally that it is the effective stress that determines the engineering behavior of the soil, like compression and shear strength, not the total stress. We know total stress at any point within the soil mass can be written as this. From this, we can write expression for effective stress. This relationship pore water pressure can actually be measured in the field. We can also calculate the effective stress. Let us consider a soil mass and try to find out the effective stress at some point below the ground at depth capital H. For simplicity, we assume that the water table is at the ground level and the soil is completely saturated. Let the saturated unit weight of the soil is gamma set. We know unit weight of soil is the weight of soil divided by its volume. Total stress at any point is equal to the weight of everything above that point, including soil, water, or overlying structure, if any, divided by the area over which this weight is acting. It can be imagined similar to the pressure, which is the force by area. Here, let's say area over which the weight is acting is capital A. So, weight of the soil above this point will be the unit weight of soil multiplied by the volume of the soil, which is the area multiplied by its height. It can be simplified to this. In our case, we have taken unit weight of soil as saturated unit. Now, the pore water pressure at this point in the soil is the pressure due to the weight of water column above it of height h. So pore water pressure at this point is also the weight of water column divided by the area. So pore water pressure similar to this. Similar, if we insert a tube or a standpipe point in the soil and observe the rise of water, because water in the soil is at atmospheric pressure, at water level will be the piezometric level. Therefore, the effective stress at this point in the soil can be given as this. The increase in the effective stress causes the soil particles to pack more closely, which results in decrease in the void ratio because of decrease in the volume of voids, and that leads to a decrease in the compressibility and increase in the shear resistance of the soil. In the calculation of effective stress, we assume that soil is isotropic. That means the unit weight of the soil is constant throughout the soil layer. But in the actual field conditions, soil structure is non-homogeneous and not isotropic and contains various defects. Write down daily learnings and express.
Okay, so I'll just sum up the video. Um, okay, if you take let's say this is our soil mass. If you consider any point on the soil mass, okay, this if you consider this element of soil mass, okay, on this element of soil mass, this height of soil is resting. Let's say h. So this weight of soil is resting and to resist this metal So total stress will be equal to all the weight on the soil. Element. Next, to resist this total stress, there are components. Component is exerted by the exerted by water. And second one is the pressure exerted by intergranular forces. So because of all the weight that is coming on the soil, this weight is resisted by the pore water pressure and the intergranular force between the soil particles. So there are three components or three forces acting here. Now, out of these three components, you cannot measure the pressure exerted by the intergranular forces. And this is also called F. But you can calculate the pore water pressure okay, the pressure exerted by water is also called as pore water pressure, or it is simply called as pore pressure. Okay, so please remember, you can also calculate the total stress. Total stress is nothing but the total weight coming on the soil element. So there are three components. You can measure total stress, you can measure pore pressure, but you cannot measure effective stress. So, and always remember, total stress is equal to effective stress. Effective stress is denoted as gamma dash plus pore pressure. So, to determine effective stress, we'll take gamma dash is equal to total stress minus pore pressure. So this is the basic principle of the effective stress. Now, why this effective stress is important? Okay, because the effective stress of the soil, it controls many engineering properties of soil. Okay, uh, uh, because of the increase in effective strength, the compressibility increases. Okay, the compression and the shear strength of the soil increases, Hence, we can say that compression and shear strength of the soil are dependent on effective stress. Now, as the effective stress in the soil increases, the compression of the soil occurs. This causes settlement of structures built on soil. If the total weight is more, then is in uh, the compression also is increased, which causes the settlement of the soils, hence the structure that lies above the soil. Okay, in the stability, the shear strength of the soil is also dependent on effective stress. You will see this in the next module. Okay, how the effective stress is dependent. Okay, how the shear strength is dependent on effective stress. We'll go into depth about this in the next module. Also, in the stability of the slopes, and while you're calculating the earth pressure, and when you're calculating the bearing capacity and the shear strength of the soil, all these values are dependent on effective stress. Yeah. Hence, you can say that it is one of the most important properties of the soil. Now, also, the permeability of the soil depends on voids ratio, and when the effective stress changes, the voids ratio of the soil also changes. So we can say that up to some extent, the permeability is also governed by the effective stress. So that's why we are studying this chapter, because effective stress is very important, because many engineering properties such as compressibility, shear strength, permeability, they are dependent on effective stress. Okay. Now please remember this: total stress is effective stress. Uh, Total stress is effective stress plus pore water pressure. Now pore water pressure is also called as pore pressure or neutral pressure or neutral stress. And you can calculate total stress, you can calculate pore pressure, but you cannot calculate effective stress. But effective stress can be calculated using this equation. You cannot calculate directly. Total pressure can be calculated directly, pore pressure can be calculated directly, but effective stress is calculated indirectly by using this equation. Total stress is equal to effective stress plus pore pressure. So effective stress will be total stress minus pore pressure. Okay. So next, we'll go to the the next topic, that is quicksand condition.
These soil grains through these voids, which we call voids. The free water available under the ground moves inside the water under the influence of gravity, which is
Uh, what is quicksand condition?
soil grains. These soil grains, when depositing in a soil mass, encloses empty space between them, which we call voids. The free water available under the ground moves inside the water under the influence of gravity, and it flows through these voids. This phenomena of flow of water, movement of water through the soil, is called seepage. We know that water moves from high energy state to low energy state. And in case of water, these energy states are represented as hydraulic heads. The hydraulic head is the amount of mechanical energy or liquid pressure available at any point in the water above datum. For the flow of water to take place in the soil, there should be a difference of hydraulic head. and water flows from high hydraulic head to low hydraulic head. Hence, we can say seepage takes place when there is a difference of hydraulic head. Water does not flow if 2 points in the water have same energy or have inadequate head difference. Water may flow even against gravity if point A is at higher hydraulic head than that of point B. As the water flows through the soil, the surface of the soil particles offers a resistance to the flow. In turn, water pushes the soil and this drag increases the interparticle forces. This force applied by the water on the soil particles is called seepage force. And because of it, pressure developed in the soil is termed as seepage pressure. When the water flows in the soil in the horizontal direction, it exerts seepage force on the soil particles in the horizontal direction. If this exerted force is strong, it has the capability to displace the soil particles in its way, and particles may get carried away by the flowing water. This phenomenon leads to the very serious problem in the soil engineering, development of channels in the soil. And this phenomena is called piping. But here in this video, we will discuss only the flow of water in the vertical direction. When water flows in the vertical direction, it has direct impact on effective stress acting on the soil particles. And what is effective stress? Soil particles in a soil mass are burdened by the weight of everything above them, which includes weight of all the soil particles above them, weight of water, and weight of any structure if present above. And because of this weight, these particles experience stress, which we call total stress. This total stress is shared by two components in the soil mass. Part of the stress is shared by the water present in the voids of the soil structure, and that is called pore water pressure. And the other part of the stress is shared by the soil grains by their grain to grain force transfer at their point of contact, and that is called the effective stress. The part of the total stress. So, total stress is equal to the sum of effective stress and pore water pressure. And the expression for effective stress is written as total stress minus pore water pressure. Stress at any plane under the soil can be given as the force on that plane divided by the area of that plane. Force on that plane is the weight of soil above the plane, and that is the unit weight of soil multiplied by its volume. Volume is area multiplied by height of the soil mass. This can be simplified to this. So, we can directly write the stress under any material as the unit weight of material multiplied by the height of the material above that point. Pore water pressure at any depth in the soil can be measured by inserting a standpipe at that point and observing the height of the rise of water in the column. Pore water pressure will be the unit weight of water multiplied by the height of the water column. We have already discussed all these in a previous video. To analyze the effect of seepage on effective stress, we take a soil sample of say length capital L and cross-sectional area capital A. The sample is placed in a tank type container that has valve at its top and bottom. First, we keep the bottom valve closed and completely fill the container with the water so as to submerge the soil. As the bottom valve is closed, no water flows through the soil, hence no seepage occurs. When water does not flow and remains stagnant in the soil, the condition is known as hydrostatic condition. We insert the standpipes at different depths in the soil and notice that water has risen in all the pipes up to the same elevation. But the height of the rise is different for different pipes. And we know the height of the water column in the soil at that depth. So, pore water pressure is different at different depths. It is the total head, which is the sum of pressure head plus elevation head, that is equal for all depths in the soil in hydrostatic condition, not the pore water pressure. If we consider the bottom of the soil sample as our datum and measure the elevations of the point of interest, we can see the sum of elevation head plus pore water pressure is same at all depths. That is, total head is same. And when total head is same everywhere, water does not flow in any direction. The total stress, pore water pressure and effective stress at different depths can be calculated for this no flow condition. Let's say height of the water above the soil sample is of height h1. Total stress at the surface of the soil will be because of this water, gamma W h1. Pore water pressure will be gamma W and height of this water column, h1. So effective stress is 0. Similarly, at the bottom of the soil sample, total stress because of water, gamma WH1, and because of saturated soil, gamma sat multiplied by capital L, length of the soil sample. Pore water pressure because of this whole water above, gamma W multiplied by the height of the water column, which is length of the soil sample L plus height of the water above, H1. Hence, effective stress can be calculated as this. And this quantity is submerged unit weight of soil. These are the effective stresses at top and bottom of the soil when no seepage occurs in the soil. Now open the valve at the bottom and let the water flow through the soil. The valve at the top is attached with a water source so as to maintain a constant level of water in the soil tank. This condition, when water is not stagnant and is flowing in the soil, is known as hydrodynamic condition. We observe the standpipes and notice that the water level in the tubes has been altered. It is not the same in all tubes as it was earlier in case of hydrostatic condition. It is now different in different tubes. The total head, that is pressure plus elevation head, at the top of the soil is higher and lower at the bottom of the soil. This difference of head at different depths in the soil clearly indicates that there is a flow of water in the soil. As we know, water flows from high head to low head. Let's say the head difference between the entry head and exit head of water is small h. Also remove this middle standpipe. We don't need it right now for analysis. Total stress distribution at different depths in the soil does not change by the flow of water, as there is no change in the overburden pressure. Total stress at the surface of the soil is stress because of water, gamma WH1. Pore water pressure will be gamma W and height of this water column, H1. So again, effective stress is 0. Total stress at the bottom of the soil is a stress because of water, gamma WH1, plus stress because of saturated soil, gamma sat L. Pore water pressure at this plane is gamma multiplied by the in H1 plus L minus head loss, small h. Hence, we can write effective stress as this. And this quantity is submerged unit weight of soil. We know the change in the hydraulic head per unit distance over which this change occurs is called hydraulic gradient. In our case, the head loss over the length of the specimen L is small h. So, flow is taking place in downward direction under a hydraulic gradient, say I equal to h by L. If we are to represent it in hydraulic gradient, we can simply write it IL from this equation. We wrote it this way because to calculate the effective stress at any depth in the soil, we don't need to insert an additional standpipe at that depth and measure its head loss, as it has been removed from the equation. Hydraulic gradient throughout the soil is stress depth Z can be given as this. If we compare this effective stress at the bottom of the sample with the effective stress in the hydrostatic condition at the same level, we can see the effective stress has increased by IL gamma W. This increased stress or pressure is called seepage pressure. It clearly indicates that downward seepage in the soil increases the effective stress or interparticle forces. This additional stress is due to the seepage pressure which acts in the direction of flow of water. When water flows down the soil mass, water tends to push soil particles downwards. Consequently, soil particles push each other, causing to increase the interparticle forces, and that is increase in effect. So, at any point below the surface at a depth z, when water is flowing with a constant hydraulic gradient I, can be written as this. Now let's reverse the situation and attach the water source to the bottom wall. Now the flow of water in the sample is in upward direction and upward seepage is taking place. We notice piezometric levels in the standpipes have changed and total head at the bottom of the soil has now become greater than the head at the top. Let's say the head difference between the two ends of the soil are small h. So hydraulic gradient that is responsible for moving the water in the upward direction is I equal to h by L. Let's analyze the stresses again. Effective stress at the top surface is again 0. Now at the bottom surface, total stress is because of this water gamma WH1 plus because of saturated soil gamma sat L. Notice that total stress is unchanged. Pore water pressure is gamma W multiplied by the height of the water column in the standpipe, which is this total height H1 plus L plus head loss small h. Hence, effective stress can be written as this. And this is submerged unit weight of soil. Here we can write this head loss as IL. Now, comparison with the previous condition shows that the upward seepage in the soil reduces the effective stress at the bottom of the soil by IL gamma W. When water flows upwards in the soil, it tends to push the soil particles in upward direction. Consequently, soil particles are lifted against gravity that causes to decrease the interparticle forces, and that we say decrease in effective stress. Now if we note head difference H keeps on increasing, it may reach a condition when this quantity in the equation becomes equal to this one, as it is nothing but head loss. At that point, effective stress in the soil will become equal to 0. We can solve it for hydraulic gradient at which effective stress in the soil reaches to 0. This hydraulic gradient is called critical hydraulic gradient and is written as ICR. When water flows in the soil in upward direction at the critical hydraulic gradient, the seepage force or drag exerted by the water on the soil particles, which pushes them up, completely balances the weight of these particles, and they seem to be suspended in the water. Soil in such state does not behave like a soil anymore, but behaves like a very viscous liquid. Soil loses all its shear strength and is no longer able to support any load. This phenomena is called quicksand. Note, quicksand is a type of sand. It is a hydraulic condition. If we remember, we learned a relationship of soil parameters. This relationship relates unit weight of water with the properties of the soil, that are soil's unit weight, its void ratio and specific gravity of its solid particles. We can rewrite it and substitute this as a critical hydraulic gradient. It is an important relationship to be remembered. If we know specific gravity of soil particles in a soil mass and its void ratio, we can calculate the critical hydraulic gradient of that soil. Gradient at which the movement of water in upward direction in the soil is such that the soil becomes quick and loses all its shear strength and is not able to support any load. We have seen in some movies that humans sink into the quicksand and die. But theoretically, it is not possible for a human to completely into quicksand. Human mass density is lower than that of quicksand soil. A human may sink only up to about his waist only if he does not panic. But if one panics, he may fall into the sand and won't be able to stand back up, and that he may die because of suffocation. So never panic if you are trapped in a quicksand. Stand still and call for help. In the meantime, also pray that elementary engineering knowledge sources prominent in the clay soils. Because first, clays have poorly connected voids, and flow of water is not as facilitative as in sand. And second, clay particles possess cohesion, which holds the soil grains together even at the critical hydraulic gradient. Boiling does not occur in coarse sands or gravels either, because to lift gravel particles against gravity, large water discharge is needed. Seepage pressure can also be written as seepage force, that is, the force applied by the flowing water to the soil structure. We know force is equal to the pressure multiplied by the area over which it is applied. This is the seepage pressure, and area of the soil sample is capital A, and this force is represented by capital letter G. But seepage force is usually expressed as force per unit volume, and it is represented by small letter J. Take a look at an example of seepage pressure calculations.
The meaning of quicksand is, let's say we have a soil mass and the water is seeping in upward direction. Effective pressure, it is always acting in downward direction. But sometimes when the seepage is in upward direction, like you have a dam. Okay, when below the dam, the water is flowing from the upstream side to the downstream side in this direction. So you can say the seepage is in upward direction because there is a head difference. Here, there is a head difference between upstream and downstream side. So here, the seepage is occurring from upstream side to the downstream side. So okay. So the seepage pressure, it is acting in upward direction. So when the pore pressure is acting in upward direction, so if the pore pressure is more, then this pore pressure, it may become at some instant, it may become equal to effective pressure. I have told you, okay, the total pressure acting on the soil, the total pressure, it is resisted by pore pressure plus effective pressure. Okay. And the effective pressure is given by when this, because the pore pressure is acting in opposite direction, this equation will become effective stress minus pore pressure. And if the pore pressure in the upward direction is very high, then at some instant they both will be same and total stress will be equal to 0. That is the total. When the pore pressure acting in upward direction becomes equal to the effective pressure, then quicksand condition will occur. The weight that is coming on the soil is equal to it won't act as soil particles anymore, it will act as liquid. So it will be forced to move upward direction, because slowly when the pore pressure is greater than effective pressure, pore pressure is greater than total pressure, then the soil particles moves in upward direction, acting as a viscous liquid. So quicksand condition, the soil loses all its shear strength and it starts moving in the direction of the flow, and that is what happens in the piping failure. Okay, the soil material, the soil particles, they are disturbed. They are thrown out of the soil mass because uh, the pore pressure is greater than the total pressure. The effect is 0. Therefore, the soil particles are uprooted from the soil mass, and the soil starts acting as a very viscous fluid. So quicksand is not a type of sand, it is a condition where the pore pressure is greater than the total pressure, or the hydraulic gradient is greater than the critical hydraulic gradient. So I'll again slightly revise this in the tomorrow's class. Tomorrow's class will be solving numerical problems based on effective stress, pore pressure, and total pressure. So be ready with your calculator, pen and paper. You will understand it much more better when you solve problems. Okay. Now that's it for today's class. We'll meet again tomorrow.